see there are a few departures from the original plan, but I think they're actually improvements rather than compromises. This topic on Unix and POSIX essential concepts, I think makes more sense to do in the first week after the mid-semester break, because it's better positioned there. We're not doing anything in that that's related to the mid-semester exam, which is probably logically our current focus in any case. And so I don't think we'll cost anything to shift that until the first week afterwards. In fact, I'm sure it's not going to cost us anything to do that. So instead tonight, we'll do what we had originally scheduled for last week, but there was some pagan ceremony on instead, so we had a public holiday. We'll do the tutorial problems from chapters 10 and 13. It won't take us very long, actually. I've forgotten that we'd actually done all the ones up to and including 8 and 9 and in the previous session. So we'll do the tutorial problems from chapters 10 and 13. Then we've got a bit of extra time to revisit any of the other tutorial problems that we've done to date, just to make sure that everyone's happy with them, because, of course, there's a subset of those that will appear as the questions in the mid-semester exam with numerical variations. After we've done that, I'll show you what I'm thinking I'd like you to do for the first part of the assignment, which is pretty straightforward, low impact stuff. And you can easily get that done over the second part of the mid-semester break if it suits you. In fact, I don't really mind when you do it, just as long as you do it before the end of the semester so I can mark it and give you some marks. The sooner you do it, the better. You submit it to me by email, and I'll mark it within a couple of weeks, and then you've got the marks. And then after the mid-semester break, we'll get into the hands-on side of the subject. Enough hand waving and some real brass tacks, and we'll talk about part B of this assignment, which will be a programming task. That all make sense? All right. Well, if we look at tutorial problems from chapters 10 and 13, we'll do those now.
If you will. See. So you guys get all of it again. Damn it, folks.
And the first one is, again, referencing just the 8th edition of the textbook, 1013. Which says, what are the advantages and disadvantages? Oh, this is all file systems, of course. Not the most interesting aspects of the subject. What are the advantages and disadvantages of recording the name of the creating program with the file's attributes, as is done in the Macintosh operating system? In fact, I'm not sure that that's still done in the Macintosh operating system. Does anyone use Macs around here? Yeah? Is that okay? You never really check. Yeah, all right. Maybe it's something that's hidden from the user anyway. They did use it for this, but I don't know whether they still do. In any case, what would be the advantages and disadvantages of doing that? So we've got some application program, a word processor, spreadsheet, game, whatever, and whenever it creates a file and saves it to disk, it stores in amongst the additional metadata that goes along with the file's contents, it stores the name of the creating program. What sort of advantages, what are the obvious advantages we get from doing that?
We know who wants the file and the file.
Well, it's not user specific, it's only application program.
There is a file which has a randomized numeric name. You still know what program uses that file, or what program makes that file.
Yes, and that helps you in through the user interface. You should be able to invoke the application program just by accessing the file itself, the data file itself, shouldn't you? Yeah. All right. So it's convenient for users who need a little bit of help using a computer. That's what Macintoshes are all about, isn't it? Well, it used to be. So convenient for users to have the association between the data file and the application program that created it buried within the data file, rather than the Windows way of doing it, the old Windows way of doing it, which is what? Yeah, through a file name extension, which you can modify anyway and break. Yeah, that's right. Okay, so user convenience would be a pretty obvious advantage in doing that, but what sort of disadvantages might there be? Sorry, mate? Yeah, you are, that's right. There's a fair bit of redundancy there, which is going to waste disk space. Yes? What other problems might we have? It kind of depends upon how the program name is stored in the metadata too. If it's stored there with a path included, and our application program is moved to a different location, well, then we'll have problems, won't we? We double click on the data file and it'll say they can't find the word processor, or they can't find the spreadsheet that created it. Even though it's installed there, it might be in a different location. That's possible, but again, it depends upon the way in which that metadata is stored within the file. Other things might impede the way in which it operates too. Things like you install some updates to the application program or a new version altogether, and it might break the association. Again, it depends upon the way in which it's done. If you're forward-thinking enough about it, and you build enough flexibility into that scheme, then the only price that you really pay is a little bit of wasted extra space, which probably doesn't cost that much. You might sacrifice some flexibility too. Like you might want to open a CSV document, normally destined for a spreadsheet application. You might want to open that in a text file instead. And it might be more difficult to do that. Again, it depends on the user interface. So we can think of a few pros and cons. None of them really serious. And again, there's not enough information in that question to really comprehensively say one way or the other whether or not it's a good idea. It sort of depends upon the way in which it's implemented, which we're not told. All right. That's an easy one. So 10.15. If the operating system knew that a certain application was going to access file data in a sequential manner, how could it exploit that information in order to improve performance? So we've got a user program that wants to open a file and read some information from it, and if the operating system knew or was made aware of the fact that that file could only be accessed in a sequential manner, maybe because it's stored on a tape device. If the operating system could recognise that, and most of them could, certainly if it's device dependent, as it would be most of the time, how might it take that information into account and improve performance? Yes, that's right. Yes, or at least parts of it. Yeah. So, reasonably obviously, we don't read just the data that the application program is currently requesting, because we can speculate that there's a good chance that it will request not just the current records or blocks from the file, but others that come in the known sequence after the current location. We don't get that certainty at all. In fact, it's not even a certainty, but we don't get that inference if the file is random access, as most files stored on, say, disk devices are. But if it's stored on a tape device and we know we can only access it sequentially, it kind of makes sense to speculate that it'd be a good idea to avoid extra I/O overhead by prefetching some extra blocks beyond the currently requested ones. What would the operating system actually? What costs would be involved in doing that? Indeed, you would. The operating system kernel, not the user level program, because it hasn't asked for that blocks yet. So the operating system kernel will have to set aside some space somewhere to store that information with the expectation that it will be requested sometime soon. And if it's not, then it's wasted. Or if it is requested, but not for quite some time, then we've got a penalty to pay there in terms of wasted memory. And of course that cost is offset against the time delay and the extra overhead involved in initiating another I/O operation. So it's all swings and roundabouts. But again, pretty easy stuff when you think about it. 10.18. Some systems provide file sharing by maintaining a single copy of a file. Others by maintaining several copies, one for each of the users, that is, processors, sharing the file. Discuss the relative merits of each approach. All right, well, there are some merits, not disadvantages. What are the merits of the single file approach? Yeah, that's right. Less resources used. We don't have to make multiple copies of it. That's a pretty clear one.
We have only one version.
Yeah, that's right. Correct. We don't have to worry about different versions and coalescing them. Yes, that's right. You don't have to worry about synchronizing updates. But what are the advantages then, or what are the merits of the alternative approach? So we've got one file stored in the file system, and we've got half a dozen different users or processors that all want to get access to it, to do things to it. What are the merits of giving each a separate copy of it?
That they can all write and read from all write to the file.
That's right. Yeah, they can all carry out concurrent operations without finding that the file is locked and inaccessible, which is definitely the case when we've only got one file. We have to lock all the other users out. So if we make multiple copies of the file, we increase the amount of total work that can be done on the file per unit time, because all the separate user processes will be able to do their reading and writing operations concurrently. Thinking back to the readers and writers problem that we looked at in chapter 5, when we looked at process management, we could probably further optimise that scheme, couldn't we, if we think about it? In what way, do you think? How did the readers and writers problem work?
So they may not have the most, like, I guess, updated information because they're all making different updates.
Yeah, that's right. Yeah, that's a problem. You've got to coalesce or synchronise all the versions. Yeah, that's right. Yeah. But even so, if we take this approach of the multiple copies approach, we don't necessarily have to make, if there's 6 different processes, for example, 6 different copies, do we? If we think about it. Why not?
Because not all 6 processes are using the map.
Yes, and not all 6 processes would be necessarily doing writing operations. Yeah. If we know that some of the processes are only going to be reading from the file, not writing to it, then those processes can concurrently share the one file. We don't need to make separate copies if they're only going to read from it. Is it likely that the operating system will be made aware of that information though? Yes. Because when we make a file system call to open the file, we specify it at the time whether we're opening it for reading or writing or both. So if the designer of the operating system was looking to optimise this multiple copies of files approaches, they would look at each user level process, and when it opened the file, it would identify if it was going to be a reading process only, and if it did, it would make that process and all others that are only going to be reading processes share one copy of the file. And then make other copies only when necessary, only when other processes want to do writing operations. So again, getting back to our example, if we had 6 processes and 3 of them wanted to do reading operations and 3 wanted to do reading and writing operations, how many copies of the file would we have to make?
4.
Yeah, that's right. Rather than 6. So with a little bit of extra work, that could be optimised. But we've still got the problem of the file system merging values that might have been written in different copies of the file. So some of the records in a file will be modified, some different records in another copy of the file will be modified, they have to be coalesced. And that's not a simple job either. All right, so easy questions on file systems. Not much to it. Chapter 13, I/O systems. Right. 13.9. What are the advantages and disadvantages of supporting memory mapped I/O to device control registers? Who's got some ideas on how we'd approach the solution to that problem? Yes?
You won't need special instructions for the I/O device?
In the case of which?
If you were using memory.
That's right. If you're using memory mapped I/O, you don't need special instructions. Is that what you were saying, mate?
Yeah.
Yeah. In fact, you can use any of the instructions that you can normally use to refer to memory locations to do I/O operations. So that gives you much more flexibility. The indirect addressing modes, for example. What's the cost of using memory mapped I/O though? Yes, mate.
It might be slower.
It is actually slower, yeah. Yeah. That's right. Usually, the execution times for the I/O instructions are faster than the instructions, or shorter than the instructions that are used to access memory locations. Even though memory devices have a natural data transfer rate which is faster than I/O devices, it's the instruction execution times that are important there. And the in and out instructions usually execute with fewer clock cycles than the than the more complicated addressing modes in some of the memory reference instructions. There's another disadvantage in using memory mapped IO. Sorry, mate? Yeah, that's right. You use up addressing capability. Once you section off a range of addresses and you say, well, I'm going to wire up some IO devices to be accessible in that range of addresses, we can't then plug memory devices in there. So we've got less memory for storing the operating system, the resident part of that when it's running, and, of course, for creating processes and running them. Ordinarily, we'll find that a mix of some sort of both approaches to I/O is appropriate. Some of the microprocessors that we'll use will assume that all I/O is done using a memory mapped approach. For example, the old Motorola microprocessors, I don't know whether they still do this, but the old Motorola microprocessors, the 6800 and 68000 series, they come with no I/O instructions, assuming that the system designer was always going to use memory mapped I/O. Whereas the Intel microprocessors had separate address space for I/O instructions. But of course that doesn't preclude you from using memory mapped as well if you want to. The original IBM PC had a whole bunch of I/O ports set aside for various devices. It's in the lecture. There was one slide there that had a few examples. But it also used memory mapped output for the original graphics adapters that they used to have on those machines. So I don't think that's the case much anymore. But the old colour graphics adapters used to be memory mapped. You used to be able to write data just to certain memory locations and it would appear directly on the screen in text mode. Not in graphics mode, but in text mode. So normally we would find there are occasions for using both types of I/O. It depends upon the type and complexity of the I/O devices that we're using, of course. All right, so that was a long-winded response to a reasonably straightforward question. 1312. What are the various kinds of performance overhead associated with servicing an interrupt? Well, answering this question is not too difficult if we just go over in our minds the sequence of activities that take place when an interrupt occurs, and identifying all of those steps and coming up with a reasonable measure, at least a comparative measure, of the overhead that's involved. So when some external device sends an interrupt to the processor, what happens? What's the sequence of events that takes place? It has to what, sorry? Yeah, it does, that's right. It has to identify the interrupting device, and it has to use that in some way to work out the address of the interrupt service routine. So there's a little bit of mechanics that goes on there straight away. The way in which the Intel processors do it is they give all interrupting inputs an ID number, and then that ID number gets multiplied by another number, and the product is the address of the interrupt service routine. The first 1024 bytes in memory for the Intel processors, there's a whole bunch of addresses of interrupt service routines. And so if we've got a device with the special interrupt ID number of 4, then that gets multiplied by 4, we end up with 16. We count 16 bytes from the beginning of memory into the memory array, and at that location we'll find the address of the interrupt service routine. Not the interrupt service routine itself, the address of it. And of course we have to jump from there to the interrupt service routine. And what happens when we arrive there?
Shouldn't we save current execution first? The state of current execution?
We what, sorry, mate?
Save the current state of execution?
Yes, we do. Yeah, that's right. And that involves what?
Storing everything stored in the processor registers.
That's right, pushed on the stack.
Yeah.
Yeah, that's right. Now, strictly speaking, we only have to push on the stack the contents of any of the registers that we're going to use in the interrupt service routine. The others will stay untouched. And that's easy enough to do if we're writing the interrupt service routine in assembly language. But if we're writing the interrupt service routine in the C programming language or something else, we've got a little bit less visibility over what gets done with the registers, and so we'll probably push all the registers on the stack in that case, just to be safe. But yes, that's the first thing that happens. We have to push registers onto the stack. And normally that's the stack that belongs to the interrupted process. Remember how processes have all got their own stacks, threads have got their own stacks? So we push registers onto the stack. If we go the brute force approach, we push all the registers on the stack. And then what do we do? We execute the instructions in the interrupt service routine. And often those instructions themselves, that sequence of instructions, will not be interruptible. Sometimes they are, but most of the time they're not. So as soon as we start an interrupt service routine, if any other interrupts arrive, it's usually the case that that interrupt service routine will not be interrupted to execute another interrupt service routine. That's usually what happens. Not always, actually, but usually. So we've got interrupts temporarily masked while that's occurring. We execute the instructions in the interrupt service routine, and then what do we do? We unstack all the registers in reverse order. That must be done because that's the way the stack operates. And then the very last register that we get off the top of the stack will be the return address. Go back to the interrupted process. So, the performance overheads are identifying the interrupting device, locating the interrupt service routine that corresponds to that device, stacking all the registers, that's all overhead, then doing the actual interrupt service routine. Strictly speaking, that's not overhead because that's just something we've got to do. But then unstacking all the registers and returning to the interrupted process, that's also extra overhead. Even some quite old microprocessors, ones we don't use anymore, like the Z80, it will come with 2 sets of registers built in, and normally use one. And then when an interrupt occurs, instead of having to stack all the registers, you just switch to another set of registers and use those for the interrupt service routine and then switch back. Which is fair enough. That was an approach that was around a very long time ago. Okay, so all that makes sense? Great. 13, 14. Typically, at the completion of a device I/O operation, a single interrupt is raised and appropriately handled by the host processor. In certain settings, however, the code that's to be executed at the completion of the I/O can be broken into 2 separate pieces. The first piece executes immediately after the I/O completes, and it schedules a second interrupt for the remaining piece of code to be executed at a later time. What's the purpose of doing that? Why make it apparently more complicated than it would otherwise be?
Maybe you mentioned a disk drive.
Yep.
You request a certain certain file,
Yeah.
then you get an interrupt,
Yep.
then the disk drives still the memory location for the file, and then you get the second, and then you can read it.
Yeah.
So you can work in between.
That's right. In
The
between the first and the second one.
rotating file thing.
That's right. Yeah. Basically, what we want to do is we want to keep interrupt service routines as short as possible, which is normally why they're written in assembly language, hand optimized code. Keep them as short as possible. Why? Well, when we were dealing with our solution to the previous question, I said that frequently when the processor begins execution of an interrupt service routine, interrupts will be disabled at that point, masked. And they'll stay that way until it finishes interrupt service routine. That's usually the case. That means that if we've got interrupt service routines which are structured in such a way that they take quite a long time, if there's a fair bit of work to be done in an interrupt service routine, it means that our system is blocking or masking interrupts for that quite long period of time, which is not good. Not good at all if we're trying to build a real-time system that is supposed to be able to respond to I/O events. So keeping interrupt service routines short and sweet is a design goal. We only do the absolutely necessary processing in the interrupt service routine, and anything which is not really that important but is related to it can be done some other time. For example, say we've got an analog to digital converter and we're measuring the voltage from a thermocouple, which is used to measure temperature. And we want to display the results of the temperature measurement on the screen as a floating point number. The last thing that we would want to do in our interrupt service routine is to be getting the data from the analog to digital converter and fiddling about with its format, converting it from an integer, which is what you get from an interrupt. So what you get from the register of an analog to digital converter, you only get an integer. Fiddling around with it, converting it into some floating point format with a certain number of significant bits and a decimal point and a certain precision, and then displaying it on the screen before returning to the interrupted program. That's the last thing we would want to do. The only thing that should be in the interrupt service routine should be grabbing the integer that we get from the analog to digital converter and storing it in memory location, and then finishing our interrupt service routine. And then some other process can do the massaging of the data whenever that might be necessary, converting its format and displaying it on the screen. So we'd identify just the absolutely necessary instructions to include in the interrupt service routine, and anything else can be rescheduled to be completed at some later time, triggered by another interrupt or some other external event. We will see when we do our hard real-time system scheduling after the mid-semester break, we'll see that interrupt service routines present a scheduling problem for us when we're trying to build real-time systems that will always meet their time domain constraints. And so we'll see why this is absolutely necessary, why it's necessary to keep interrupt service routines as short as possible, only do the absolutely essential operations within them, grab the bit of data from the I/O device, in the case of an input device, store it in memory, and then that's it. Do everything else later. just do the essential operations in the interrupt service routine and let everything else take place later on. Absolutely essential. Okay. Oh, that's actually it. Yes. All right, so that takes care of some reasonably easy questions from IO systems and final systems. And with that, we've got everything covered for the semester exam. However, if there's any other problems that we've done in the previous weeks that you'd like to go back over, then now's a really good time for us to do that. While you're thinking about that, while you're going back over the previous tutorial problems, let's check out the first part of the assignment spec, which is nice and easy. I'll read all this out. You've probably seen it before, but I'll read it all out just to make sure that everyone is looking at the right thing. We've got a critique of a technical paper, worth 10 marks. An important skill is being able to distill good quality technical summary from a document that might contain extraneous pieces of information. It's often the case that specialised scholarly papers don't always present neatly and coherently the essential nature of the topic they're trying to portray. This situation is frequently worsened when the document under study is one that's attempting to sell a product or an idea. And being able to extract primary messages and commenting on them is the focus of this exercise. So, to quote British comedian Warwick Davis, we like the sound of logic slicing through bullshit. Not to say that any of the papers that we're going to be studying here are bullshit, they're not. However, what we want to do is to look beyond what they're presenting as superficially and really make an informed commentary on the subject matter. So what I'm suggesting you do is look at the papers that we've got to you as candidates. Pick one of those, one that sounds like it might be at least moderately interesting to you. The way in which you can do that is by looking at the abstracts, essentially. So pick one of those. Oh, yeah, that would help, wouldn't it? I've got a real good view of it here. Yes, so we've got a collection of papers here, and you can have a look at the abstracts for those. And that will give you a bit of an idea of what they're about. That's just one example there, and there are quite a few others. But what I want you to do is to critique the paper, maximum 5 pages. Don't make your report 5 pages if you can get it done in 3, that's fine. But ensure you do this. Include a summary of the contribution that the paper makes. That's not to summarise the paper, right? That's summarising the contribution that the paper makes. The technical merit of its contents, whether you think it's applicable to mainstream operating systems and applications, because a lot of this stuff is potentially interesting, but frequently of modest commercial or industrial practicality. Whether or not you think the key points made in the paper are really justified by the evidence. So frequently the authors will say, this is the best thing that we've seen for quite some time, but again, that might be borne out by results of experiments that they've published, or it might not. And then anything else that you think is relevant. So, importantly, I'll put here, and I'll read this bit out too, demonstrate your ability to critically analyse what's being presented in the paper, not just regurgitate the contents of it. Right? I've already read them, so I don't need you to tell me what they're about. Instead, I want you to tell me what you think of them in terms of these points here, at the very least, and why. embellishing things to a point that you think might need to be called into question. And that certainly is the sort of response that I'd like to see, where necessary. If you happen to have an interest in some other associated technical field, in other words, if you've got an interest in something else which is operating systems related, but and you found a paper which is not in this list, you'd like to study and critique it instead, then I'm happy to entertain that idea. But I'd like you, if you want to do that, to email me the paper first, so that I can have a bit of a look at it. And then if it's worthwhile, then yes, you can go ahead and do that. I think just emailing me your report, again, maximum 5 pages, will be all that's necessary. So is that clear? Nice and easy, non-technical, but an important skill that I think you should be capable of doing by now as senior students, and one which I'm sure you're going to get asked to do professionally, if you haven't already, many times. So a little bit of extra practice here won't go astray. Anyone got any questions on that? All right. That's all pretty clear? Oh, yeah, sorry. Well, whenever you want. Just before the end of the semester. Yeah, whenever it suits you. I'm not going to be too worried about that. You get it to me, I'll mark it, and you get the marks back. Yeah. So if you do it over the mid-semester break, fine. If that doesn't fit for you, then just sometime in the semester, as I say, I really don't mind. Remember that we've got to have everything supported. Well, I want to have everything in the grade book, or whatever they call it now, grade centre, whatever it is, by the end of the week after the last teaching week. Right, so by the 12th of June, I want to have the grade book full of everyone's marks for the assignment, and the mid-semester, of course, will already be there by then. So I don't mind, whenever it suits you. And yes, we'll have a technical assignment to work on after the mid-semester break. There'll be some programming to do there. Okay, so yeah, back to the tutorial problems. Are there any tutorial problems that we want to revisit now? Anyone got any niggly-naggly doubts about any of the ones that we've done? If you can do them all, then yeah, you'll be in and out of the mid-semester exam and in no time, with nothing much to worry about. Yes, mate?
6.10 of the 9th group.
Right, so that's 5.9. Why is it important for the scheduler to distinguish between IO-bound programs and CPU-bound ones? That's the one.
No. Explain why spin blocks are not appropriate
single processor system with a lot of used multi-processor system.
Did you say 6.10?
6.10, yeah.
From the 9th edition?
9th edition.
That's strange. Oh, yeah, this is a different form. Yeah. All right. Yes, yes.
That's right.
Interesting questions, but yeah, that's not on our menu. Yes. Yeah, good idea.
I'm going to start every question with the addition. So let's have a look. It's like a UTS room number.
So we're going to do 512, but we're going to do round robin with a quantum of 2 instead of 1. It says round robin quantum 1. And we're going to do round robin, yes, 2 instead of 1. All right. So we've got those processes there. I can hopefully get all this in the one picture. Yes. Okay. So they're assumed to all arrive at the same instant. That's in the order P1, P2, P3, P4, and P5. So we'll start with P1. That's got an execution time of 10. So here we'll have P1 and P1. And then we've got P2, execution time 1. And at that point there, that process terminates. So we've got a new rescheduling event to occur here. I'll put R here for rescheduling event. So process 2 has completed. Process 3 starts, and it's got an execution time of 2, which happens to coincide with one that's going to be preempted anyway. Then P4, which has got an execution time of 1. So it terminates, and we automatically invoke the scheduler and dispatcher again. And then we've got P5, which has got an execution time of 5. Then we're back to P1, then P5, then P1, then P5, and P5 finishes there. So these are all rescheduling events. And then we've got P1 and P1 to finish. That makes sense? Yeah, so you were worried, what happens when the quantum time is longer than the execution time? Yes, that's right. All it does is bring forward the rescheduling event. Yeah. Yeah. No worries? remember how we define the turnaround time? How's the turnaround time defined?
Isn't it when it arrives compared to when it finishes?
Yes. End time minus arrival time. That's right.
It's pretty
Yeah.
common sense.
Turnaround time, end time minus arrival time. Yeah. I can't remember. They're all like these. They're something to do. Yeah. So, there'll probably be a question like this one in there, with different arrival times and different execution times and different priorities. Asking you to do special things. Yeah. I can't remember. It's usually about two problems from each chapter, roughly. Yeah, it was a couple of months ago I had to give the exam last semester. I can't remember what it looks like.
Steve?
Yes,
So in terms of studying for this, would you recommend we just go over the tutorials, or do you
absolutely.
go over the lectures and?
If I was you, I'd look at all the tutorial problems, make sure I can do them all, and then put my feet up. All right?
Sure.
That makes sense?
Yeah.
All right.
Sorry, I've got one from 720.
Which one, mate?
It's 720, but yeah,
720.
720.
It's a banker's algorithm one, is it?
Yep.
It's basically just all the cheats and it's just going to ask like the cheat stuff again. That is basically to identify if you did not any of the other tutorial questions or any of the other challenge questions. Make sure there's no spam.
Here we are, 720. Yes.
I just wanted to know,
Yeah.
you know, for when you calculate, when you cancel out the 1520 to go to the next process, so your available vector, you cancel it and you go to the next one. If we have an incoming process of, let's say, 0420,
Yes.
that comes in, and then we want to start calculating the available vector for the next time.
Yes.
How do we calculate the available vector for the next time? Is what I wanted to know.
All we do is we subtract 0, 4, 2 and 0 from 1, 5, 2 and 0.
Yep, and then if we wanted to go again,
Yes.
how do we calculate it?
It depends what request arrives,
Yep. Okay.
but our available vector then is going to be 1, 1, 0 and 0.
1, 1, 0 and 0.
All right, which doesn't leave us much,
Yeah.
does it?
No. So you see that 1, 1, 0, 0?
1, 1, 0, 0.
That's the number.
It's
How did you get that number?
1520 minus 0420.
Yep. Okay. Yes.
All right, so 1100.
Yep.
That's
okay,
all we
yep.
got left.
Yep.
Then it's saying, okay, if we get requests that arrive that are bigger than that, we
Yeah.
can't do them. Simple as that.
Okay.
All right, therein lies. That's the first test
Yep.
that presents a problem.
And we check that with the needs.
That's
Vector.
yes. The needs vector says what maximum requirements each of the processes have.
So I would check this number to
Yes.
check which process runs next against the need.
Yes,
Okay, and then if I get this, will run P2 next.
it could do.
Okay, and then if I get this next, my issue
Yeah.
becomes how do I get the next available?
Yeah, all right. Well, what happens is, P2 can't run because
Oh, yep, sorry,
it
okay.
requires 1, 0, 0, and 2. However, P0 can run.
Yep, perfect.
All right.
P0 runs.
P0 runs,
Okay.
and P0 is currently allocated a 0, a 0, a 1, and a 2. So these ones here will be given back.
Okay, yep, so it's 1, 1, 1, 2.
Correct, mate?
Okay, perfect.
That makes sense?
Yep, that makes sense.
And then of course, other requests might arrive,
Yep.
and we can first of all again see whether we can afford them
Yep.
out of this.
And-
That's the first test.
So check that with this, and then if it does,
That's
go
right.
back, add, and yep,
That's
okay,
right.
Perfect.
That's
okay,
right.
Yep, no worries.
Yeah. But the point of that last part C there is, even though we can make that request, even though that's right.
Yeah.
Yeah.
Okay, got it.
So it's that we shouldn't because it may send us into deadlock, right?
That's right. We shouldn't because we've got concerns over the system safety. Remember how we define safety?
Yeah.
Yeah. So there are safety issues. But yeah, when a process terminates, mate, we get from it all the resources that it holds. Yeah, no problem.
Okay, what else? New question. This answers, I don't know why.
Yeah, revenge. See what's going on. What's floating in the market.
You gotta think, like, you gotta think,
Yes.
like, I had to pause and then go back and do it again.
Can I just?
Oh shit.
Take from the back, because otherwise you're gonna get confused. Okay. So
Tell me when it's like water can
you're gonna want to start. Yeah.
No, it's cool,
Okay,
it's
so I
fine.
went back.